The next problem involves conservation of energy when there's a frictional force involved. A spring with a spring constant of 1000 newtons per meter is attached to a 10 kilogram mass and is stretched 0.5 meters past its equilibrium point. If the coefficient of kinetic friction is 0.3, A. What is the speed of the mass as the spring moves past its equilibrium point? B. How much work is done by the force of friction? So let's draw this picture. So we have a spring, okay, and it's stretched, attached to a 10 kilogram mass. M equals 10 kilograms, right? And it's stretched past its equilibrium point, right, by x is equal to 0.5 meters. Okay, so that's the initial. And then the final is that the spring is returned to its equilibrium position. So x here is equal to 0. Alright, so that's the final, that's the initial. Mass is still 10 kilograms, and the velocity here is equal to question mark. Okay, the initial velocity, because it's at rest, is equal to 0. Okay, alright, so let's do this. Alright, so in this case, the initial energy is equal to the final energy plus the work due to friction. I like to know this as the work as W sub F. Okay, so the work due to friction is just going to be equal to basically the force of friction times the distance, right? Which in this case is just going to be x times x final minus x initial. These things denote absolute value because I just care about what the total distance to travel needs to be. Alright, so the initial energy, I, well, let's write this again, EF plus W sub F. So this value here, EI, is simply equal to 1/2 mvi squared plus 1/2 k, which is spring constant, xi squared, that's the potential energy of the spring. This is going to be equal to 1/2 mvf squared plus 1/2 k x sub f squared. This is the final potential energy of the spring, plus the force of friction times basically xf minus xi, where this is the absolute value, right? The distance that the frictional force acts upon. Okay, so let's just solve this. So Vi is initially 0, so it's going to be 1/2 m times 0 squared, that entire thing is 0, plus 1/2, k is 1000, xi is 0.5 squared, is equal to 1/2 times 10 kilograms, so it's 10 kilogram mass, times Vf squared plus 1/2 times 1000. The final position, because it's back at equilibrium, is a 0 squared, so this entire thing goes to 0 again, plus the force of friction, which is going to be basically the weight of the object, normal force, m times g times mu, okay, which is the coefficient of static friction, kinetic friction, or mu sub k, times, let's make sure I write it down here, times xf minus xi. So this is going to be basically 0 minus 0.5 absolute value. So this is going to be 0.5 here. So let's write this down a little neater. This is 1/2 times 10, which is 5 Vf squared plus mg. So it's going to be 10 times 9.8 times 0.3. And this one, the absolute value is going to be 0.5. Okay, so when we work this thing out, this is going to be plus 98 times 0.3 times 0.5. This turns out to be about 14.7. Right? And this entire thing is plus 5vf squared is equal to, this is 1/2 times 1,000 times 0.5 squared. This is a quarter. A quarter times 1/2 is 0.125 times 1,000 is 125. Okay? And so we can compute what VF has to be now. So let's subtract out 14.7 on both sides. Right? And so this is going to be 120.3 is equal to 5VF, squared, divide by 5, divide by 5, right? And then this will give you basically 120.3 divided by 5 equals VF squared. Take the square root on both sides, right? And so what this gives you is that VF is equal to something like about 4.7 meters per second. It's actually 4.69. 4.7 is pretty close. All right, I hope this was helpful. Okay, again, basically, in order to solve conservation of energy equations, you write down what the initial situation is, write down what the final situation is, and in this particular case, because we're dealing with friction, the equation just modified it slightly. The initial energy is equal to the final energy plus the work that is lost to friction. All right, hope that was helpful.